Thank you very much for being here. So my name is Clement Blaudeau. I'm going to present the work I've been doing with Natarajan Shankar on verified Packrat parser interpreter for parsing expression grammar. This work has been done at the SRI while I was in a research internship during my master's studies at École Polytechnique. So let's take a look at the table of contents, the overview. First thing, we're going to talk about parsing and parsing expression grammars, why we chose those kind of grammars, and the way we analyze what we call Wellformed grammars, kind of things. Then we're going to move on to the parsers themselves and the system, and maybe the most interesting idea of this presentation, which is to use what we call a reference parser. And then we'll move on to the semantic interpretation to build real use case parsers. And then a little demo, some proof statistics, reference and future work, and finally the conclusion. So first thing first, what is parsing? Parsing, you may all be familiar with it, is basically four things: an input, a grammar, a parser, and a result. If you fix the grammar inside the parser, you have what we call usually a parser. If you let the grammar be anything that you give alongside the input, you have a parser verifier. If you don't give the input, you have a parser generator, all those kind of ideas. Here we're going to talk about a parser interpreter. So we'll always consider that we give both the input and the grammar. But in the slides and in the illustration, I may use the word parser for parser interpreter everywhere. So if you're going to do a verified version of this thing, you may want to use grammars that ensure some strong properties. And that's why we chose to use the parsing expression grammar developed by Brantford. Those expression grammars are basically following three main goals. They are simple. They use a restricted choice of operators. They are expressive because you have mutually recursive operators, mutually recursive patterns, sorry. And they are unambiguous. And that unambiguity gives you the first interesting result, which is the fact that you have unicity of the possible parts. There is only one possible parse given a peg grammar. But you also have this problem of termination that you can have in all left recursive parsers, which is also present in the peg grammars. So how do you ensure that you have this unambiguity property? Basically, what you will be using is that you have those operators that are close to what you can find in most grammars. But for the choice operator, you have a prioritized choice. So you're going to look for the second pattern only if you have a proof that the first pattern fails. And the same for the star operator. You're going to do it in a greedy way. So you're going to try to find this E pattern as much as possible, and then have a proof of failure before moving on to another pattern. So what does that look like in PVS? It's basically a data type, so really easy to define. You have those constructors, and you have those identifiers. You may be wondering why some basic constructors are missing, like the range operator, for example, or the plus operators. Those kind of operators are basically can be emulated using those basic cases. So we are just going to focus on the basic cases. But in the real implementation, actually, there are all the operators that you may think about. So that's the PVS code. And then there is a very important part in the static analysis of a grammar, because as we saw, there is this problem of termination. And to resolve that problem, you will basically need to define properties on the grammar. So what are the main properties on the grammar? Basically, we have three main properties. And a grammar can have either one of the three, or two of the three, or all three properties. Is that you can succeed without consuming any token. So that's the danger property, because as you have greedy operators, and if you succeed without consuming anything, you can create infinite loops very quickly. And then you have success with consumption of tokens. So that's really okay. No, don't worry about this one, because you're sure you're going to terminate. And you have the can fail property. Actually, you need all the three to be able to compute the dangerous one, which is the P0 property. Once you have computed the property, finding a fixed point basically in the set of properties, you can ensure that there are no infinite loops and that basically every patterns of your grammar only uses patterns that are above it before you are sure that at least one character was consumed. So that's a part that is not, that is very important, but is not well explained here because all the details are in the paper. I invite you to take a look at them. But once you have well-formed grammars that ensure termination of parsing, you can move on to define what is parsing, actually. What is parsing? And there are basically two ways of looking at it that are kind of the same difference between big step semantic and small step semantic. Parsing is either a relationship between input grammar and the result, or parsing is a computational behavior, so the computational path of the parser alongside every choice that the parser made trying to parse the input. And even though the relationship, the big step semantic is quite interesting definition and quite intuitive one, we chose to go for the small step semantic in order to be able to have an effective proof of the behavior of the parser. Because you don't have to trust the fact that it produces good result, you have the actual behavior in your hands to check that the parser behaved correctly. So that's the idea of using those abstract syntax trees that represent the behavior of the parser. And one thing I want to mention is that you keep the failing branches. You're looking for some character, you fail because it's not there. You keep the branch, you have the proof of fail before trying something else. So you have those failing branches in the tree. And once you have, once you define this tree type, you can have a notion of meaning. So the tree can either represent a success, a failure, or is undefined. So you can say, for example, that those branches are failing trees, and you don't know for the whole tree. But once you have this notion of meaning, you can define a notion of well-formedness. That is, this tree represents an actual parsing computational path. And once you have this notion of well-formedness, you have back the idea of uniqueness between input grammar and a computational path. There is only one possible computational path. That result you add with the big step semantic, you also have it with the small step semantic. What those results look like in PVS, so they're pretty easy to see. So, for example, if you have one tree and there are two possible grammars, two grammars that are that corresponds to that tree, then they must be the same grammar. There is only one grammar corresponding to a given tree. The same for the input with the small detail that you start at a given point and you end at a given point. And the main result of the uniqueness of the tree, given two trees that correspond to the same input and same grammar, they must be the same tree. So again, you have this unicity, input, grammar, and a well-formed tree. Once you have this result, you may want to move on to the parser specification. So you know how to define the computational path of the parser. So let's take a look at exactly what a parser does. So the parser, which is actually a parser interpreter, takes a bunch of arguments. So basically the most important one being the set of non-terminals. That's the set of patterns you're going to look for. And then the current non-terminal you're looking for, the current grammar node inside the non-terminal that you are actually parsing, the input strings that never changes, the starting index, and then this technical thing that is the starting index when you started to parse the current non-terminal it's needed for termination. But most of the parser specification is done on the output type of the tree. That is something that you can do in PVS, is to have very complex types, and we use this to specify that the parser behaves in a correct way just by saying that if the output tree verifies a certain number of properties. So first and most important one, the output tree is well-formed. That means that all the small checks at every node ensures that the computational path is a correct one. Then the output tree starts at the expected position that you gave an argument to the parser interpreter, is true to the input and true to the grammar and true to the input, and then verifies that it fails or succeeds according to the property that you add on the grammars. The termination is ensured by a lexical order on this for tuple. Basically, the most complex case is this one, is the technical thing with the non-terminal starting index. So I won't get into more details, but please ask questions about it if you want. But you get to the main two results that are interesting when you're trying to build a parser. You have the soundness and completeness result. The output tree, as we saw, is well-formed. And a well-formed tree always has a meaning. So it's always a success or a failure. So your tree is always producing a sound tree. Your parser, sorry, is always producing a sound tree. And you have this completeness result. As there is only one possible tree that corresponds to the given input and grammar, and the parser is finding a tree that corresponds to the input and grammar, then the parser is actually finding the only possible tree given the input and grammar. So you have both those two results. And then when you've built such a parser, you may wonder, okay, maybe we can do some optimization. Maybe we can change the way the parser behaves and try to have a more efficient one. So that's the idea of using a reference parser. The basic idea when you're trying to prove the behavior of a parser is that you have this set of properties, specification, maybe the soundness and completeness results. It could be quite hard to prove, actually, that the parser does what you think it does. And so it may be interesting to try to factorize the proofs and have a reference parser that behaves in a naive way, very simple to prove the properties on it. And then the other parser, you just prove equivalence with the reference parser. And that could be much easier than doing the full completeness and soundness proof. So that's maybe one of the most important ideas. And so let's look at an example. The most simple optimization you can do is memorize results, so you don't compute the same thing 2 times. This makes you go from exponential to linear complexity. And so in this case, you have the Packrat parser, and that you prove the equivalence with the reference parser, and you get all the properties of the reference parser almost for free. And the equivalence, you can just put it in the type. You said that the Packrat parser produces a tree that verifies this equality, that is, it is equal to the reference parser called on the same argument. So it's really the simplest case. You said that it produces the same thing. But you may wonder what happens if we try to play with this notion equivalence and build other kind of parser that produces different trees. And that leads us to the idea of semantic action. The problem with the IST trees, as we saw, is that it contains the failing branches. And those failing branches are not interested for the user. Basically, he only wants to know what succeeded in the parsing and not all the failing branches. So the user is not interested in failing branches, but also the user is not interested in the tree structured by the underlying peg grammars. The user wants to, for example, if you're passing HTML, you don't want to have a tree that corresponds to the underlying peg structure of the grammar. You want the DOM tree. So the user should be able to provide constructors to build a custom data type during the parsing. But if you do that, the direct equality, as we had with the Packrat parser, it does not hold anymore because it's not the same tree. So you need to define a notion of equality modulo a semantic interpretation. So basically, if you have a tree, for example, the gray boxes corresponds to numbers. So you parse 1s and 5s and fails. So that gives you number 15. And the same for all the arithmetic expressions. So you have this semantic interpretation of the full tree that contains the failing branches. Then you can say, OK, I have my grammar and my input, and I compute the reference parser, and then I do the semantic interpretation. And that's the same thing as using my semantic parser. So that idea to play around this notion of equivalence, to have more complex notion of equivalence, modulo an interpretation of the trees. And that gives you the semantic parser. So let's take a look at a simple demo. So,
You're shadowing the screen again.
Sorry?
You're shadowing the screen with your elbows.
OK. So if we try to parse this very simple expression, I hope everyone can see. So we get a semantic result with the custom data structure that I provided. But if we try to use the reference parser, then we get the same thing, but with all the failing branches. So it's a much bigger tree. And that is useless in practice, of course. OK, some proof statistics. For only the semantic parser that is also linked with the reference parser and all the rest of the proof, you have approximately 329 proofs with 4,000 commands inputted in PVS. But the most interesting figure is that 88% of those proofs are what we call TCCs, so type check conditions. So most of the proofs are done in ensuring that the parser has the correct type. And there are actually very few explicit lemmas or explicit theorems. I don't have the exact number, but as you can see that there are 4,000 input commands. You can see that. I would say, in my experience, that maybe 30% were automatic, and we had to do some work for.
You really put them up in your types, right? Because in other PVS formalizations, probably almost all of them would be automatic.
Yes, but when you work with recursive data types, sometimes the automatic method are not able to understand that they should expand on one side of the equality and not the other, and so the automatic method don't work that well. Some those kind of proofs. So a very quick reference work. So the most important papers. But of course, you have all the references in the paper associated with this presentation are the one from Brian Ford, because he invented peg grammars. So without his work, of course, there are no peg grammars. And also this TRX parser, which is a COC verified parser of peg grammars. And also a quick note on the future work. So the main three things we'd like to work on is that once you have this semantic tree, you may want to, for example, parse something like the size of what's coming next is 50 bytes. And then to ensure that you pass something of size 50. So you'd need to extract the information and put this information inside the grammar while parsing. So that would be supporting semantic action on the grammar during the parsing. So that's a huge thing because you have to change all the architecture. And then we'd like to write a parser of peg grammars themselves so that user can provide a file that describes the peg grammars and get the PVS implementation out of this and not write the constructor of the grammar himself. And that's linked with the third point, which is to improve the user experience in building real use case parsers, which is not very easy for now. So a quick takeaway. We developed a new approach to the peg static analysis that I haven't developed much here, but you have all the details in the paper, especially a more computing approach to this problem. Then we have this idea of using the full trees, even with the failing branches, which are like the small step representation of the parsing, and to build upon those trees to get the property. Then you have this factorization of the reference parser, and then to build like a chain of parsers that are equivalent to the reference parser on which you will prove all the properties. And then the way we implemented the semantic interpretation. So I tried to let a few minutes for questions. Thank you very much for your attention, and please ask questions.
Minutes for questions.
First, I have two questions actually. The first one is about, you said there's only one grammar for each parsing tree. And that looks a strange statement. Can you clarify?
Sure. So actually, we
Because
have
if you're parsing a string that doesn't contain some element of the language, then the grammar is not going to talk about that.
Yes, that you're absolutely right. And actually, what this lemma ensures is that the part of the grammar that was expressed in the tree is unique. But all the patterns that weren't used in the tree, you don't know about them.
Okay.
So what the result you get is that the part of the grammar is the same, not the full set of patterns that you could have used.
Okay, that was what you meant.
So that was a very, very good question.
Okay, the second question I have is about memoization.
Sure.
You said that you had a proof that the memoized version was equivalent to the reference parser.
Yes.
But it looks like this kind of result is actually more general than about parsing. Did you use a general approach for working about memoization? Or did you have the feeling that you were the first one to look at this kind of problem?
No, this memoization technique actually was not developed by us. It's also the work of Brian Ford. We developed the Packrat parser. But what we've done is just to have a set of results that we update during the parsing, and every result has the same property that if you call the reference parser on the same argument, you get the same output. And then when you're trying to compute something new, you check that you don't have it in the pre-computed results before outputting it. So it's like an ad hoc approach, I guess, but the idea of memoization is not from us at all.
I understand that, but the idea of doing the proofs, and I was just wondering whether you were using a generic tool that was already provided in the PVS environment for doing this kind of proofs.
No. We wrote the Packrat parser in fully, and we did the proof on it.
Thank you very much.
And by the way, you have all the code is available on GitHub, so if you're familiar with PVS, you might be able to look at it and understand it. It's commented out. So.
All right, let's thank the speaker.